Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. We had been discussing about the applications of stable water isotopes in our previous lecture, and in this particular lecture also we are going to see some more applications using stable water isotopes. So, I was discussing this in the last lecture where we use delta 18O values as a paleo temperature proxy, because delta 18O values has a dependency with temperature, and using carbonates from our records. So, from the marine deposits, if we take the carbonates and we date them and we use those carbonates and do the delta 18O, and with some corrections we can find out what was the temperature at that particular oceanic conditions. So, how the past how the past ocean has changed its temperatures. Okay. So, it is a very robust proxy for paleo temperature determination. And not only does it work with ocean carbonates, it also works in terrestrial ecosystems. Now, in terrestrial ecosystems we deal a lot with this thing called speleothems. Okay. Now, what are speleothems? Speleothems, like in cave environments. So, imagine you are in a cave, and specifically this cave is in a karst topography. That means where there is a lot of carbonates happening. So, it is not just any cave, it is a cave in a karst topography. That means there has to be carbonate rocks there, and in this cave when the water drops, okay, so there will be lot of cracks and fissures and all these things. So, when the water drops, the water that has a lot of carbonates dissolved in it drops slowly, right. It will drop slowly, drop by drop. What happens inside the cave, outside the cave, there is a difference in temperature and there is a difference in pressure and air conditions and all that. Now, given the high concentration of carbonates, what happens is, as soon as a little bit of pressure change and temperature change happens, the carbonate starts precipitating. Now, this carbonate, if it precipitates as if it is hanging from the wall, okay, it is hanging from the roof of the cave like this. Okay. So, this is the roof of the cave, okay, and these are the hangings. So, this is the hanging, this is the hanging. Okay. So, it is hanging from the roof of the wall, from the roof of the cave. So, these particularly are called the stalactites. Okay. These are called the stalactites. Sometimes it so happens that when it is falling from the top, similar deposits are also forming on the ground. Okay. So, there are a variety of deposits that we can see in actually a cave. So, there can be stalactites, there can be straws, there something can be column, there can be a flowstone, there can be a stalagmite. So, stalagmites are these kind of structures which are formed from the ground. So, they are growing from the ground, and as the water drips, so the the carbonate starts forming. So, it is like a tiny narrow kind of pointy hill like structure growing from the ground, but it is growing from the top to bottom. It is not growing from the bottom, it is just because the water is dripping along its sides, it just has that kind of structure. And if it is coming from the roof of the cave, it is called the stalactites. So, these stalactites and stalagmites has been often used to refer to back to the delta 18O of the precipitation. Why? Because when these carbonates are forming, so precipitation, just like condensation, is also considered as an equilibrium process. Okay, that is, it is happening at that is in equilibrium with the water. So, whatever was the delta 18O value of that rainfall, the carbonate that is precipitating from that rainfall will have the same value. That is my theory. Okay. So, the delta 18O of the speleothem will be same as that of the delta 18O of the precipitation or the rainfall from which it got formed. Okay. Now, once I know the delta 18 of the precipitation or the rainfall, I know that it is a function of temperature. There is a direct relationship between the delta 18O of meteoric water with the temperature, and it is specifically very good in mid to high latitudes, or if it is in the lower tropical areas, subtropical areas, equatorial areas, then that relationship becomes very good with the amount of rainfall. So, there is a dominance of function of temperature as we go to the mid to high latitudes, and there is a dominance of the amount of rainfall in the lower latitudes. Okay. So, that is my second theory. Okay. The third thing is that if we have, if the speleothem, if we can date it, okay, if we can date it, and then we do the delta 18O compositional analysis based on the particular ages, we will see some variations, and that most likely reflects how the temperature of the rainfall has varied with time. What do you mean by the rainfall temperature? The rainfall temperature is directly related also to the airfall temperature. So, the air temperature is also directly correlated with the speleothem delta 18O. So, we know that the speleothem is correlated with the delta 18O of the precipitation. The delta 18O of the precipitation can be correlated with now the mean annual air temperature. So, if it is a hot region, of course, the rainfall will be a few degrees lower than that particular region, but it will have a similar warm temperature. If it is in a very cold region, it is in high latitudes, then it will be much cooler, the temperature will be much lower. So, given this kind of relationship between the air temperature and the rainfall temperature, we can find out what kind of variations we expect in the air temperature at that particular age, because these speleothems can be many thousands of years. It is not happening overnight. This slow dripping of water, slowly precipitation of carbonates, this can actually date back to a few thousands of years or few tens of thousands of years. So, therefore, how it has varied in the few tens of thousands of years, these speleothems can give us very nice data about how the temperature has varied in that particular region. And we have a empirical relationship with the speleothem delta 18O values and the mean annual temperature, that there is a difference of 0.35 parts per mil with per degree Celsius change in the annual air temperature. Okay. So, such this is an example from the crevice cave which is in Missouri in USA. The data has been taken from this particular paper, and here we have this crevice cave where 4 stalagmites were collected from different locations. So, stalagmites are these structures which are developing from the ground. Okay. But again they are formed from the dripping of the water or the precipitation. Okay. So, these are different stalagmite samples. So, there is one which is CCDBLL, one is DBLLS. So, they are the red points, one are the blue points. This is another stalagmite, this is another stalagmite. So, there are 4 stalagmite samples, and what they did is they did the dating of the sample. So, they have another method for dating. So, they dated the sample and they also did the delta 18O value. Okay. So, this is the delta 18O value, you can see the change in the range. Okay. So, the using, and you can see the kind of variations it has, it is almost like a zigzag pattern. So, it has been very useful, and it has shown some very useful changes, and it shows how the cold during the cold periods we have the much negative values, and the warm periods where we have much more positive values. So, this kind of records help us understand how the air temperature has varied, and this has also been used. Okay. It has been also been complemented with the deep sea ice record in the same time period. Okay. But this is not using stalagmites, this is using some other data. So, they here also we plot the same time period, the delta 18O, and we see okay whether this kind of high air temperature matches with the ice forming or so here it is the ice volume that they have shown. So, it is a deep sea delta 18O values that they have plotted, and if the deep sea delta 18O values are rising, it means that the sea ice the sea is getting more and more delta 18O. That means more and more 16 oxygen is getting trapped on the continents. So, if the 16 oxygen gets trapped on the continent, then only the 18 oxygen in the deep ocean gets enriched. So, it is a huge change. Okay. So, a huge amount of ice formation is required to shift the delta 18O value to the more positive values, right. So, these are the time periods when the ice volume has increased, right. The deep sea delta 18O has become increased. Okay. So, the ice volume here is decreasing and the ice volume here is increasing. Okay. So, just imagine if the ice volume is increasing on the land mass, what is happening? The ice mass is trapping all the 16 oxygen value. Okay. If the 16 oxygen is getting trapped, then the delta 18O values are also getting decreased in the terrestrial in the terrestrial system, but it is getting more and more positive in the oceanic system. Okay. So, therefore, by combining we see if the warm periods that I am noting here is also matching with the warm periods that I am noting here. Okay. So, this very nicely showed us the usefulness of the speleothems and how we can use it with the sea delta 18O values and see okay if the ice if we are seeing basically the same warm periods, and if we can see if it is having any common time periods during which such noted incidents are there. So, it is not only from one particular data set, it is from other samples also, and here we have all the dates and they have been checked with the other proxies from other reservoirs as well. Now, let us move into oceans. Since we started seeing some ocean data, it becomes very useful to understand how oceans are working, right. How do oceans change the delta 18O values? Now, the delta 18O values vary only about 1 parts per mil in the deep waters. As you can see here, the total variation is only 0.5 from here to here, the total variation is only 0.5. Why? Why are the deep sea oceans not as variable as the surface oceans? It is because first of all it is not even in it is very well mixed system. It is the surface waters, there might be some stratification due to salinity, due to density, due to temperature and all that, but in the deep water the ocean masses are very well mixed, and the variations due to changes in temperature, due to changes in salinity, due to changes due to any other mixing is very less. The chance of any particular large scale processes that is happening in such a scale that it can change the delta 18 of the water itself, it has to be magnanimous process. Okay. Because imagine here the amount of water that is there in that particular reservoir. So, it needs a huge event to change the delta 18 value. Only the values get very muted even if some changes are happening on the surface. As we go down in the depth, the changes get very muted. So, you are seeing the changes in very very small. So, the changes here is in 0.1 parts per mil, right. So, that is why when we are working with deep sea ocean data, the maximum variation that we observe is only 1 parts per mil, and that also they are at nearly constant at 34 to 35 PSU, that is the salinity value. And even with this kind of variation, that even with such a low variation, it provides a huge information about how the ocean mass is accumulating, how in the different regions of the oceans circulation is happening, how, where is it mixing, where is it upwelling, where is it downwelling, which ocean masses are particularly mixing to give a particular ocean current. So, the mixing of the ocean mass, a huge information can be derived from the delta 18 data. Even with this 1 parts per mil variability, we can try to understand how the deep sea is mixing, how it is accumulating or generating new currents. And what are the parameters that controls these 1% variability? Let us just start looking into this. So, there are not only oxygen that we use, which is the as we use as like a thermometer because of its relationship with temperature and its huge application in the field of paleo temperature determination, and therefore, we need another proxy, and we often use carbonates as the proxy. So, oxygen both in water and in the carbonates. So, both in the water form and in the carbonate reservoir, what is the delta 18O? Using that values, we use these isotope data like like reading the temperature. Okay. And possible variations in the delta 18 of surface ocean water, it can lead to an uncertainty of around 10 degrees Celsius in temperature estimates. Why? Because we are we are trying to read past temperature, okay. But the delta 18O of the surface ocean, they can be determined, they can be subjected to much more changes other than temperature. There can be rainfall, that means there can be rainfall happening that is changing the delta 18O of the surface ocean. There can be freshwater discharge near to the coastal areas, near the bays and all. That can cause changes in the ocean, surface ocean delta 18O values. There can be other evapotranspiration effects that can cause change in the delta 18O values. So, there can be several other processes due to which we feel that the delta 18O value of the surface water of the ocean, that means the surface water means where the wind is touching the ocean, that is called the surface water of the ocean. Okay. So, where the wind and the the atmosphere and the oceans meets, that is the surface of the ocean. So, using the delta 18O values of this particular ocean water can have certain drawbacks, okay, and it can have to large uncertainty in our temperature. It's not absolutely useless, but it may have certain errors, and this is mostly due to the addition of either fresh water, basically either it can be ice melt water from near the poles or from the rivers, whatever, the stream water and all that is coming in, or due to the other variations with weather. That can be, there can be storm, there can be rainfall, there can be certain other very hot and humid weather where there is a lot of evaporation going on. So, therefore, the delta 8 values have changed. So, these kind of processes can also alter the delta 8 values, but we can start therefore depending on the deep sea delta 8 values. Therefore, we use the delta 8 values of the deep sea. And what are some of the main questions that we are interested in understanding when we are using delta 8 as a source tracer, as a time tracer? What are the main questions that we ask? The first question or the most important question is how the composition of the delta 8 itself has varied over the geological time scale. Because if we are not sure how the delta 8 of the water itself has varied, then we do not have something to refer to when we are comparing it. So, we need to know. So, when we were talking about when we are talking about the strontium isotope record. So, we have the strontium isotope record, and then we are looking at certain records in present day, and we are matching it with the strontium isotope record. So, for the delta 8 we still need that kind of oceanic record to understand how the temperature has varied, how this carbon dioxide concentration has varied. So, anything where we are applying delta 8 we need to understand how it has varied over geologic time scale. That means over millions of years. And it is one of the most ongoing unresolved problems still in earth science. The main challenge is because even though recent years data can be said with certain confidence, as we go back in time, it becomes more and more difficult to get proper records, because we are dependent on what? We are dependent on water itself. And when we are talking about water, where is this water coming from? So, we look into water that is trapped in between the sediments. So, we look into sedimentary rocks, we see if there is any trapped pore water, and this water, if it comes from dating that it is several millions of years old, we see if that water can be suitable for delta 8 values, because often it so happens that once you extract that, it has to be done very properly. So, given the fact that these trapped water volumes can be extremely less. So, just imagine it can be like a very small, like if you see a drop of water, so it can be like 1/10th of the drop of water, or it can be even low. So, using such low volumes, you have to use it for both dating the water, and you also have to use it for deriving its isotope composition. So, it becomes very challenging to find such samples, proper samples, and if we are dependent on carbonates. So, the other reservoir, detrital carbonates, which can be several millions of years old, like more than 500 million years old and 600 million years old, then that also, like the suitability of those samples has to be verified before it is applied for these kind of studies. So, therefore, we do have data. It is not that we do not have the data, we do have few data, but it is an ongoing research, and what theoretical considerations suggest that if the ocean water had to vary, then it would require a huge geological event, a major event. So, such an event that would that would change the isotope composition of the water itself. So, it has to have to be a huge global event. Okay. Such events are very rare, and therefore, its probability to happen in the past is also very low, but it cannot be totally neglected. Okay. So, we from our from our theoretical understandings, we know that given the huge reservoir, we need a huge event that can change the isotope composition of the ocean. But from the mass balance studies, from some data, we have some information. The mass balance, that means, what do we mean? That mass balance means how much water is now there in the ocean, how much water is now there on the continents as lakes, as rivers, as ice, everything, if it returns back to the ocean. So, if the continents become absolutely dry, all the water that is there on the continent, it returns back to the ocean. What will be the ocean composition? So, that kind of mass balance suggests that the delta Etino values of ocean would just get lower by 1 parts per mil than the present day in ice free time. What do I mean by ice free time? That means all the melt water from the poles, from the continental glaciers, they have all melted. They have all melted and returned back to the ocean. So, therefore, the present day, if I consider it as 0 parts per mil, then in the past I expect that the ocean water value would have been minus 1 parts per mil. But our data from certain marine sediments, from certain other sources has shown us that in the geological past we could have had values as negative as minus 15 parts per mil. Okay. So, water trapped in the marine sediments, okay, as fluid inclusions and all that, people have studied that water and have been able to determine the isotope composition, and as low as minus 15 parts per mil was there, therefore indicating that in the past we would have seen a huge variation in the water isotope data. Now, let us see what causes, what kind of processes can cause a delta Etino of ocean to change. Here we plot the delta Etino with the salinity. Why? Because in ocean these two are very important factors, since this is our parameter of interest, and another significant parameter is the salinity of the ocean. And when we plot the data, present day, past and everything, we see that the salinity and the delta Etino of the ocean has a linear correlation. Same thing, the salinity and the delta D value of the ocean also has a linear correlation. Why do they have a linear correlation? Okay. Let us see why do they have a linear correlation. The reason is that if it is, there are two processes. First thing is evaporation. So, if it is evaporating, if water is evaporating, then what will happen? 16 oxygen will get enriched in the vapor, and therefore, the ocean will get enriched in the 18 oxygen, it will remain with the 18 oxygen while the vapor gets enriched in 16 oxygen. So, therefore, my delta Etino value of the ocean, will gradually increase, it will gradually increase, and with evaporation what will also happen? Saline water will grow more and more saline, right. With evaporation, as the water mass itself, as the water volume itself is getting low, water that is evaporating is not evaporating with the salt, right, the salt is getting remain behind. So, the salinity is increasing gradually. So, during evaporation we have a gradual increase in both salinity and in delta 18O value, therefore, we have such a type of curve. But if there is addition of fresh water, just the opposite. So, there is a lot of addition of fresh water going on. What is happening? All the 16 oxygen that was trapped in the glacier ice mass is now getting released and coming back into the ocean. So, when this 16 oxygen now gets into the ocean, its ratio increases, the 16 oxygen increases. So, the delta 18O value will now decrease because the influence of the 16 oxygen. So, the delta 18O now decreases and it decreases much rapidly, as you can see this steep slope. But the salinity also decreases, but it has a much shallower effect on the salinity as compared to the delta 18O. Delta 18O rapidly decreases. What happens if it freezes? Okay, there can be another impact, that it is freezing. Okay. What do we mean by freezing? That means from the water ice is getting formed. Now, it is not in the continent, it is in the sea. That means, this is sea ice. When the poles, the water gets very cooled, extremely cooled, then that is kind of slowly the sea ice starts to form. Okay. But what will happen is, now this is a kind of an equilibrium process, it is not strictly equilibrium, but it is a very slow equilibrated process. It does not have to undergo the evaporation condensation kind of process, it is just freezing. So, when that kind of process is happening, the delta 18O of the ice and water, that means of the sea ice, okay, of the sea ice and the sea water, the delta 18O difference is only 2 parts per mil. That means, if my ocean water is having a 0 parts per mil value, then my sea ice will have a minus 2 parts per mil value. Okay. So, that is what it means, that the del 18O of ice and water is 2 parts per mil. But this ice will not incorporate any salt in its structure. So, all the salt will get pushed out of the crystal lattice. Okay. So, the salinity of the the salinity, what will happen, the water will get very rapidly, the water will get more and more saline, but the delta 18O value will not change as much. So, here you can see that kind of effect, okay, where the delta 18O value is decreasing, the freezing is happening, and with the freezing the delta 18O value is changing very shallow. There is a very shallow, there is very low change in delta 18O values, but the salinity change is much higher. So, it is almost like a horizontal line, but it is not absolutely, there is some changes with delta 18O values as well, but we see more changes in salinity. Okay. And another with evaporation is precipitation. So, if there is precipitation happening, then also there will be fresh water input, right, but that fresh water will be not as negative as ice melt water or the polar fresh water. Okay. So, therefore, the decrease in the delta 18O value of the ocean will be much shallower. Okay. So, this is polar fresh water and this is rainfall just happening in the equatorial region, which is basically evaporated ocean mass. So, with this I come to an end to today's lecture. We are going to discuss more about this in our next lecture. Thank you.